Well, that's okay. Okay, so the question. Give you just a very short timeline. Toss a ball of mass m downward at 8 meters per second, hits the ground 20 meters lower. Okay? And we want to find how fast it's going when it hits. Well, I'll use delta y instead of delta x, or whatever symbol you want to use there, delta s. If you want to use delta x, okay, there's no reason you can't have the x axis pointing downward or upward. There's a solution. Now, one bit of advice, do it with symbols and plug the numbers in later. Okay? But how much does v squared change when you do this? Well, v squared changes from v naught squared to vf squared. Okay. I mean, v squared starts out at what, at 64 meters squared per second squared, right? And it goes up to something after it's fallen 20 meters. Okay. And falling 20 meters is going to take 2 seconds, so it's going to get up to 28 meters per second. Square of which is 784, something like that. Anyhow, you can put numbers in it, but you don't need the numbers to understand what's going on. You can reason it out with symbols, and it's less messy if you reason it out with symbols and then plug in the numbers. So I'm kind of advocating that. You've seen me do a lot of stuff where I just put the numbers in and, you know, the quantities and do the units and all that, because I want you to see that mainly how the units work out. Also, there's some advantage in doing that in a lot of cases, because you can think about what those intermediate numbers mean. So sometimes you want to do that. But you also want to think about the overview, which is just how do you do it symbolically. Okay. And then learn from the process what you can. Okay. And now this is vf squared minus v naught squared. Okay. And what's vf squared minus v naught squared? In this equation, vf squared minus v naught squared is a times delta y. Now, nothing here is specific to free fall. This could be any uniformly accelerated situation. Okay. One warning. Change in v squared is not the square of delta v. Okay. If your velocity went from, say, 10 to 30 meters per second, then v squared would go from 100 to 900 meters squared per second squared. It'd be a change of 800 meters squared per second squared, right? If you take your delta v, it's 20 meters per second, 10 to 30. In the square, that's only 400 meters squared per second squared. So this would be very different from this. And there's simple algebraic reasons for that, so you really kind of want to try to work that out. I'm not gonna. It's just, this is VF squared minus V naught squared. Okay. Delta V is the square of VF minus V naught, which is VF squared minus 2 VF V naught plus V naught squared, because you're squaring a binomial. Here, you're not squaring a binomial, you're squaring the individual numbers. So hopefully that rings a bell. Anyhow, think about it. Okay, so we have this. Okay, now. What is F net delta Y? Well, you know, you got delta Y, 20 meters. What's F net? Talk about it for a minute. Okay, first, you know, it's pretty obvious. F net equals MMA. It's MA delta Y, right? So right there is A delta Y. Okay. So what A is, I'm switching gears on you a little bit. A is F net over M, right? Okay, well, we noticed. Okay, we have this A delta Y here. We have an A delta Y here. What I'm going to want to do is I'm just going to replace A by F net over M. In fact, I'm not going to do that. You're going to do that. Correct? Replace A by F net over M. Got this expression for VF squared minus V naught squared delta V squared. Replace A by F net over M and solve for F net delta Y. What do you get? Now, circle here and here, so clearly this is the equation we want. So we have so if I want to get just F net delta Y, which is what I'm trying to solve for, I multiply by M over 2. So the M here divides this M, the 2 divides this 2. And we get, I'm going to write it out this way. Okay. A lot of you know, have maybe had the M over 2 times all this. Maybe had M times this squared minus this squared over 2. Maybe had something else, and maybe didn't quite get to it, but it's pretty straightforward out. So nobody's going to have any trouble with that. So make sure you can do that. Because all we've done basically is we've taken this equation that everybody knows and has used a number of times in the homework. We've taken this equation and we've rearranged it to give us this, which is totally equivalent. And that is, the meaning of that is a change in your V squared, right? And then we use F net over M instead of A. You got this, okay? We could also write this then as ouch. We need to write with a different figure. One of the little drawing things, I don't know what. Well, 1/2 MVF squared minus 1/2 MV naught squared is the change in MV squared, isn't it? Because MV squared starts at 1/2 MV squared starts at 1/2 MV naught squared, ends at 1/2 MVF squared. So there's the change in 1/2 MV squared, right? Well, we got names for these things because this shortcuts a lot of calculation with the equations of motion. Okay, you replace the equations of motion with a simple concept of work and energy. Okay, the connection is this is work. This is change in kinetic energy, which is a change in 1/2 MV squared. If kinetic energy equals by definition 1/2 MV squared. That's a big deal. This is the essence of the work energy theorem. Now, this only applies in this case to motion in one dimension. Work done by the net force equals delta KE. Now, I say this is work. I'll use the symbol W net because this is net force times your displacement. Okay? Make sense? All right. Let's apply this. Figure out with machine. If S is your position, by S I mean the position of the system, where the motion is actually rotational. System's kind of rotating like we talked about earlier. And I could use omega for position, but that could be confusing at this time. So I'm just going to use S. Okay. Where S is greater if the thing is further along this. So S is greater if M2 is descending. Okay. In any case, S is the position. What's the net force? Well, the net force is M2G minus M1G. You might not be able to read that, but you've seen it before, so hopefully you, the chalk kind of hit a rough spot. But M1 didn't come up very well, maybe that's a little bit. Okay. Makes sense. Now, if we give V naught and delta S, and we find VF. Using this. You can certainly do it using equations of motion. But what I want to show you is it's very much easier to do it using the work energy theorem. All right, now this is unfamiliar, you know, we're trying to pull something. We're trying to get a clear focus on something that comes out of all this, and it's not that difficult. You're going to do it. And we're getting there. So I said, you know, first of all, where is the work done by the net force? Somebody said, well, it's there. Well, yeah, that's in general, but we don't have a delta Y here. We've got a delta S. But that's the same thing. It's work done by the net force. And that's clearly the net force multiplied by delta S, because that's how we define work in general, okay? So we could actually then write this more generally as F net delta S. And your text will drop the E on kinetic energy. I've written it out several times, and now K just means kinetic energy. Okay? So sometimes I'll write KE, but sometimes I'll just write K. A little neater with just a single symbol. Less writer's cramp. Less space on the page. Okay? And this is for one-dimensional motion. If you go into 2 dimensions, you just make a slight modification, and I'll write that down. We're not going to deal with the 2-dimensional case. Yeah, we might. We might not deal with it today, though. Okay. So if you know the 2 masses, and you know how far it's supposed to go, it's real easy to figure out the work, right? I give you the masses, let's say 5 kilograms and 4 kilograms and 3 meters. Okay, well, 5 kilograms times G, 4 kilograms times G, you subtract, you're going to get 9.8 or round off 10 newtons. Okay, and times how many meters did I say? Whatever number of meters I say. Okay. Okay, makes sense? So that's really easy. Really easy. Much easier than solving those equations, and that's not hard. Okay. So it also gives you a different way of thinking, where you don't mess much with acceleration. It makes the thinking process smoother. So it's a concept that comes directly out of analysis of motion. Okay. It makes life easier. Gives you a more comprehensive way to think about things. Okay, so here we have it. Now, if I'm also given V naught, what do we do? Well, change your kinetic energy. Well, kinetic energy has now been defined as 1/2 mv squared, and never forget that for the rest of your life. I mean, how can you drive a car efficiently if you don't understand kinetic energy? It's what gasoline gives you through the thermodynamics of your engine, and we'll worry about that later. Okay. And the mechanics of your engine, which you probably know better than I do. Okay. So here's your change in kinetic energy. Here's your work done by the net force. If I've given you V naught, then this quantity here, which if you know M1 and M2 and delta S, you just calculate in a couple of milliseconds, okay? Very simple to calculate for the given information. What's M? We got M1 and we got M2, but what's M?
Minus M2.
All right, let's say we'll discuss it. Okay, the answer I got was M2 minus M1, but no, that's not M. M is the total mass of the system. Okay, that's the difference of the two masses there. Point blank here. Okay, so we know M. We can add M1 and M2, that's easy. And now we've got a number for M. I don't want to put those numbers in just yet though, because what are we after? We want to find VF. Do we now have enough information to find VF? Well, we're also given M1 and M2. Let's just be explicit about that. So is there anything in these equations that we're not given? We know M2 because that's given. We know M1, that's given. We know G. Presumably we're in the vicinity of the surface of the Earth. And if we aren't on a different planet, we'll figure out what G is there. Just time with pendulum. Okay. Of no what. And I told, say, we're given delta S. So let's say we know this, and this. What else do we know? Well, let's say I said you're given V naught, so we have this. M equals M1 plus M2, so we know this because we know these. What's left? What is it that we can use this equation then to find given that information? Yeah, VF. Okay. And it's an easy solution. So I would recommend you solve that equation for VF, plug your numbers in, and think about what the numbers mean. Okay. You do want to think about what M2G minus M1G means. You want to be aware that that's the net force. Okay. And you want to be aware that this M you got here is the sum of the two masses, but you will be. All right. So all we have to do is solve that, where we know everything but VF. And that would allow us to solve this if I give you the mass. Okay. It's fairly easy to find using this because you already know the acceleration. If you know acceleration is given as something else, goes ball rolling down an incline, you have a different acceleration. Still use energy in kind of a subtle way. There's a complication of the balls in the incline. because the ball itself has particles that are moving rotationally. They suck up some of the energy. Now we'll get to that later. Don't worry about it right now. Okay. That makes sense. So it's a very simple consequence of what we already know about uniformly accelerated motion. All right. Now, in general, it's a dot product. Work as a dot product of F net vector with a delta S vector. So for example, we got a mass in free fall. So it's experiencing force negative mgj. Okay. Now imagine the rock thrown off the cliff. It goes up, comes down, lands somewhere much lower than where it was started from. Okay. So your delta S, and really we're talking about an increment of displacement. Okay, but let's just think some short displacement. You chop up the path into a bunch of short little segments, each one being some vector delta S. Okay, that makes sense. So I can draw a picture of that. You know, here's your path, and we chop it up into short segments. We already kind of did this before, maybe even of equal length, but they all have different orientations, different directions. Okay. And you figure out F net dot delta S for every one of these. Now, let's see, how many of those did I just make? About 20. Okay. Which one of those segments do you want to use? Okay, so somebody just told me 10. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 increments. There's a 10th increment. I think that was this one. I'll call that delta S10. Okay. If I put that together with my mg, or my negative mgj, okay. Say that this distance here, just to put some numbers on it, because it doesn't hurt to think in terms of a few numbers. Say this is 100 meters, like it was that one problem in their assignment. Okay. And how long is this? How long is that vector? If the scale is, this is 100 meters. How many meters long is your delta S? So okay, let's use 5 meters. Okay, so now we've got a delta S. And it's a vector, so I should have put an arrow over it in the first place, and I didn't. Delta S10, 5 meters at what angle? So, okay, so we made some estimates. So, okay, so this is 5 meters at negative 50 degrees from horizontal. It's just an approximation because from one end of this increment to the other, the direction actually changes a little bit, right? Okay, but we're just doing a ballpark discrete approximation. Write it out with symbols like you do Riemann sum and take limits and stuff like that. and you get an integral that tells you everything. But right now, we just think about discrete sums and approximations. Okay. So how do you picture the dot product? Well, the dot product is this vector, magnitude of this vector times magnitude of this vector times the cosine of the angle between them, right? What's the angle between these? Well, if it's 50 degrees from horizontal, then it's 40 degrees from vertical. Cosine of 40 degrees is a little over 0.8. No, a little under 0.8, sorry. Notice a ballpark 0.8, but it's a little less than that. Which means you'd have 4 meters as the projection of this vector onto this one. Now, what's that mean? This vector is vertical, so any projection is going to be horizontal from the tip of this vector. And if I enlarge this picture a little so I can actually label it, I've got this direction. I've got this vector, magnitude 5 meters. I'd luck out, maybe I get part of this chocolate isn't full of grit. Okay, we've got 40 degrees here. The projection of this vector on this vertical line, which is part of the vector I've drawn up here for the weight. Right now. It's approximately 4 meters. Okay, a little less than that. I'll say it's approximately 4 meters. And I could also have a vector here that's a vertical projection. It would be 3 meters. Okay. This 3 meters is not directly relevant to the dot product because the 4 meters is your 5 meters times the cosine of the angle. That's very approximate. It's actually somewhat less than 4 meters. The only part of this vector that's in the direction of the force is the 4 meter component. 3 meter component is perpendicular to the force. Force only does work on the part of the displacement that's parallel to it. Okay. You can also say, from the point of view of the delta S vector, the only part of the force that does any work on it is the component of that vector in this direction. It's the same either way. If you understand dot product, you understand what I mean. Okay. If you don't, go back and review it, get a little more familiar with the dot product. It's easy enough to compute with, but to understand what's going on here, you need to understand it. And the dot product just says, take the component of one of the two vectors in the direction of the other one, multiply that component by that vector. Okay. That's the same thing as saying take the magnitude of this vector times the cosine of theta, which is the component here. Okay. And multiply it by the magnitude of that vector. That's what it is. If you don't understand that, if you've been through linear algebra, you should really understand that, because 90% of what you did, especially in the latter part of the course, we do orthonormal bases and stuff like that. It's all dot products. When you do Graham-Schmidt, we do with Graham-Schmidt. You take two basis vectors, you throw away the part of one of them that's perpendicular, that's parallel to the other one, and use the part that's perpendicular. Now you got an orthogonal, a pair of orthogonal vectors that are part of your basis, and then you just keep doing that. Now, that's just all I'm gonna say about linear algebra, because not everybody's had it. If you've had it, that should click. If it doesn't click, you probably should go back and think about it, because that's really important. In many areas of engineering. It's not required for this course. I just mentioned it because it gives you better insight. If you just use what chapter 2 told you about dot products, that's plenty for this course. But if you put a bigger context, that's great. Okay. The thing we take from this is put an arrow over the mg so I don't have to write negative mgj. That's what the vector mg is. Okay. Only that component has work done on it. Okay. Let's say you're trying to move a car or a truck. Okay. And you get a bunch of people and you have them all leaning up against the truck. Got enough people and they're big enough, if they lean in the right direction, the truck is going to gain kinetic energy. Okay. And let's say the truck is on a hill where it's almost ready to start moving. So it doesn't take that many big people. Even a bunch of small people might be able to do it, as long as they can reach the bumper. Okay, with their shoulder. Whatever they want to lean with. You don't want to lean with your head. So comfortable. Okay, so you have a bunch of people leaning on the truck. Now, is it going to be more effective if they're leaning on the back of the truck, like the tailgate, or if they're leaning up against the front door? Which way is the car going to move? Obviously, if they're leaning up against the tailgate. If they're leaning against the front door, they're not pushing in the direction the car will move. You know, the wheels are set so they wouldn't move forward. So you're not doing any good by leaning on the door, right? Well, it's only the component of force and the direction of motion gives you work. Okay. Now, if you're pushing the thing, you ever push the car, 50 yards or so, you get out of breath because you're doing work and you're having to metabolize stuff that requires air, oxygen more specifically. Okay, so you got to breathe harder and your heart has to pump faster. Okay, just start pushing cars around for an afternoon. You'll understand that you're doing some work. Okay. Now you can go leaning against cars' doors all day and you might stiffen up a little bit, but you're not doing any work. Your heart's not going to start pumping for that. Okay. Or you can push on the side of it. You might stretch your muscles a little bit and your heart might actually react to that, but you're not going to get out of breath. Okay. You might have a stroke from the blood pressure if you push hard enough and long enough, but you're not going to get out of breath. I guess if you have a bad enough stroke, you'll be out of breath permanently, but it's a different use of the terms. Okay, so don't be doing that. Okay, well, that's an important idea about work. It's thing that it's exerting a force through distance. Okay, or force through displacement. Yeah, we can use it to do a lot of stuff. And that's what chapter 7 is about. Also, chapter 8. I think I've got the chapter numbers right. Your text breaks the study of work and energy into 2 chapters. Okay, where you study the effect of a force through displacement and use that to solve problems. Same type of problems you solve using the equations of motion, but in a conceptually bigger but simpler manner. Okay, like here, I want to know how fast this thing's moving when it hits the ground. It turns out if I add up all these arrows for the displacements, some of them are going up here, right? Which means the force is in direction opposite, the displacement's in direction opposite force, which requires that work be done, which lowers the kinetic energy. And you know, if something goes up, it slows down, okay? Then it comes back down and gains as much as it lowered by the time it gets here. And all the delta S components, vertical components of your delta S, from here to here, they're all up because the delta S will be going up like this, right? And then from here to here, they'd all be down. And the ups and the downs add up to 0. And then you have all the downs from here to here. Okay. So if you add up all the delta S components for all these segments, basically you get the negative 100 meters. So you just do it all at once since your force is constant. If it was a variable force, like if you're approaching a magnet, this wouldn't be constant. It might even change direction as well as magnitude. But in this simple case, you just get the work is it's just going to be F net delta Y. This is a delta Y. You get a delta Y for every segment, and they all add up to this. Does that make sense? We could draw that picture. I draw a little bit of it. Here we go. Okay, so let's say we got 3 segments here. We have a delta S here, we have a delta S here, we have a delta S here. From this one, we have a delta S to delta Y. Because when you project this on the direction of your force is in the Y direction, P and Y's. Okay. And then, you know, there's a delta Y from this one, and there'll be a delta Y from this one. So that's delta Y sub I, delta Y sub I sub 1, delta Y sub I plus 2, if you wish. Okay. Using traditional subscripts. All these delta Y's add up to 100 meters. So you can say that the work done by the net force is F net delta Y, which equals a change in kinetic energy, which is this. If you're given V naught, doesn't matter what the angle is. Okay, if you just know how fast it's going here, that's all you need. You don't have to figure out angles. You don't have to figure out V naught sine theta, V naught cosine theta, the components, and analyze the components separately. You can figure out how fast it's going here. Okay. Because if you know the mass, you know the velocity, you know F net, which is negative mgj, and you know your total delta Y. The only thing you don't know is VF, and there you have it. Okay. Now, when you analyze this for homework, incidentally, some people made the mistake of only figuring out the final velocity for the vertical motion. Well, you have a horizontal velocity that's unchanged, right? Then you have some vertical velocity when you get here, and people figured out the vertical velocity, forgot about the horizontal, or tried to add the vertical and the horizontal. You got to use a Pythagorean theorem. You have velocities in this direction and this direction. It's vectors, they add as vectors, they add like parallelograms. Here's your VF. Okay, Pythagorean theorem. VF squared equals VFY squared plus VFX squared. I think that you made that mistake on the homework. Change your thinking a little bit. Some people did. And you just don't add this to this. Okay. Just give you the, that gives you something that doesn't even have physical interpretation. All right, well, back to this. You understand how much simpler this is than the analysis that you did on that problem, right? If you simply understand that W net equals F net delta Y, which equals delta K, you know F net, you know delta Y, you know V naught, and you know the mass. You don't even have to know the mass because the mass is a factor of V net. The mass is negative mgj, right? So you have the mass here, here, and here, divide it out, it goes away. All right. Let's apply that to okay, I got a bunch of ideas. I want to look at all of them, see which one I want to do first. And we're going to get that one to do. I like the pendulum a lot. I keep thinking pendulum. That's what I was thinking before I looked at this. Yeah, I think we need to do pendulum. Okay. Now let's say this thing is swinging in one direction or another. Remember, you know, I wanted to clarify one thing in this picture so I could savor this. And we'll be able to start using this board again from a week ago. When I put the coordinate system like this, or I put the coordinate system like this, doesn't matter which way I put it if you have a small angle. If the angle's small, then it's pretty much vertical, horizontal, either way. Okay. And that whole analysis works out either way. So that's all I wanted to say about this. If you look back at that, keep that in mind. And I don't want to get into too much more of that. But now for the pendulum, what I want to do is I want to say, okay, if V equals V naught at position theta, what is V when the thing is vertical? Well, work done by the net force is delta K. This thing changes position. When it swings down, it's lower than it was here. Okay. Now the motion is mostly back toward the equilibrium position, but it is also getting lower. It's analogous to this situation, but the only thing that matters is your change in y. So the change, or the work done on the pendulum is mg delta y. Now, you might say, okay, well, it's a negative mg and delta y is also negative, right? It goes lower. So these are parallel, so I'm just going to write them as if they're both positive. But you might want to say, if you want to think of this direction as negative, then you say it's negative m or mg times negative delta y. Okay? But we're not going to worry too much about that right now. That's going to be 1/2 mvx squared minus 1/2 mv naught squared. Okay, you can divide through by m, so I'll just kind of cross that out, right? And you end up with vf squared equals 2 delta y plus 1/2 v naught squared. Again, we never had to touch an acceleration. Just using the idea of work energy. Again, the work is okay, mg, the weight vector is always straight down. So if you break this up into little segments, you're going to have a case just like this, where in each little increment, your mg delta s, mg dot delta s is just mg times delta y. It comes down to that. I'm using this more or less as an illustration. What you have to understand, and when you get more comfortable with the work energy theorem, you just say, well, it's lower here, so gravity did work on it. Every little segment has a downward component, and gravity does work on the downward component. Okay? You add up all the downward components, you just get this distance, this displacement from here to here. And this is just a change in the kinetic energy, which is always 1/2 mvf squared minus 1/2 mv naught squared. It doesn't matter what the acceleration is in between. We eliminated acceleration mathematically when we did that solution that I asked you to do. Okay. So that's kind of neat. That's not a formula you memorize. It's just, this is just a direct two-step result, algebraic result. And then you learn to interpret it. Okay, another case. You got a low friction cart rolling down the incline. Starts here. Ends here. So this is your position. We'll call this S naught and SL. You got some delta F, which you can measure. If it's 30 centimeters or 60 centimeters, whatever. Okay. Now I'm going to make these vectors though. So if I subtract S naught from SF, So your delta S, and you might not totally understand what I mean by these two vectors. In any case, your delta S is, well, I'm going to write that there. Here's your vector delta S. If y is your vertical coordinate, then the y component of delta S is just yf minus y naught. This angle is theta. And the y component, okay, well, delta S is a vector, like the vector from here to here. And the y component of that, you just multiply by the sine of theta. And you probably would have put a negative sign in front of it also. Because your y goes down. You multiply that by the weight of this thing, and you get the change. Or you get the work done by the net force. Okay, we're going to do some of this in lab. We'll work it out. But the main thing I want to do is kind of introduce the idea of energy. Those who've had it in the homework appear to have a handle on how to do free body diagrams, and if you make mistakes, you know, pennies on there and the frictional force is in this direction. No, okay, frictional force is back toward the center. Read my note if you did that, because more than one person did. You know, little things like that, but you have the idea of a free body diagram. Just don't make up forces. Just because it feels like something's happening here doesn't mean it is. That makes sense? And I think you'll be okay on the problems. And if you have questions on some of the problems, we can take a quick look at it Friday, but we've got a lot of stuff we want to measure to get into this idea of working on it. One more comment on it. No, we're out of time. I'll save my comments. How you doing, time? Okay. If you have questions in the homework, email, and I'll have computer access 24 hours a day, but I sleep somewhere, so but I do check it pretty frequently.